Hi, everyone. It's time for another team training for the Oklahoma Housing Needs Assessment Project. And the lesson today is about map projections. And this is a topic that, you will often face in ArcGIS in particular, but it's really a larger part of our prototype model flow chart here, so it's definitely you're going to learn how to manipulate projections in the GIS software, but it's also a part of the data processing of data, and part of creating maps for output, either static maps or web maps. You may want to display them with different projections. Okay, so let's start with a little review about spatial location. And if you watch the GIS basics video, this is a little bit of a review here, but whenever we're talking about mapping something, we're mapping it on the Earth's surface. Okay, and the Earth is generally a sphere. Okay, and this conceptual diagram kind of shows how you can define any point on the Earth's surface using two angles, right? The longitude, right, which measures how far east or west of the prime meridian that goes through Greenwich you are on the sphere. And then the latitude angle, which measures how far north or south you are above the equator. And those 2 points will find any point on the surface. Now, there's some complications with this, okay? So the first thing is Earth is not really a perfect sphere. It's what they call an oblate spheroid. And different geographic coordinate systems have been developed to estimate that. So the Earth sort of bulges at the center because it's spinning like a top, right? And there's more centrifugal force around the center. Also, there's more land in the northern hemisphere than in the southern hemisphere. So there's kind of a misdistribution of mass. So these different geographic coordinate systems use different mathematical models to try to estimate that, right? And different ones have been developed over the years. And GIS actually has a large database of them stored in the program software. Now, that's all well and good, but we are often interested in taking that geographic coordinates and projecting them onto a flat surface. And we do that because we want to show it on our computer screen, or we want to print it out or something like that. And so, you have to do a mathematical transformation from the geographic coordinate system to a projected system. And there are many of these. Here's sort of the three most common families: the planar, the cylindrical, and the conic projections, right? And so the way you kind of imagine this is like you have a piece of paper that you want to project the Earth's surface on, and there's a light bulb in the center, and the Earth is transparent, and it projects it, right? And so with a planar projection, the plane intersects at one point on the surface of the Earth. A cylindrical one, it intersects at there's a line that intersects. The same with a conic, but here the plane is sort of warped to come to a point, right? And you will see different projections for all of these. Now, another thing about planar projections is it allows us to convert degrees, minutes, and seconds, or angles, into distances, which is very helpful, right? Because most people don't think in degrees, minutes, and seconds. They think in like meters or miles or something like that. So a map like this one, which shows units in millions of meters, for instance, instead of degrees, minutes, and seconds. Now, when you do the transformation, from the geographic coordinate system, which is trying to fit the Earth's shape as close as possible, and these all probably have some distortion already, but they don't distort things nearly as much as these planar projections do. And whenever you do a planar projection, you're going to have some distortion. So this example here on the left is an example of a map that you may be familiar with, the Mercator projection. And I just noticed I have the labels back asswards here on this one. So just bear with me. This is a conformal map. In other words, it preserves shape, but it distorts the area, right? And so you can see that Greenland up here looks much larger to Brazil, but in real life, Greenland is much smaller than Brazil. And what's happening here is as you do the projection, it's a planar projection, and the area is getting spread out farther and farther, the farther away you get from the point that intersects. And like in this case, the intersection is on the equator. So the farther north or south you go, the more distorted the area becomes. But the shapes look correct, okay? Then over here, this is an equal area projection. This is a sinusoidal projection that preserves area. And you can see here Greenland is its correct size here. It's smaller than Brazil, but you're seeing that you've given up for area. Now you have distorted the shapes of things, right? So like here's North America here, and you can kind of see, that like it looks all sort of cattywampus, cattywampus, real technical term, but skewed, right? It looks distorted. And so what map makers have done is they've come up with ways to try to, balance the conformal and the area. And here's a Winkel triple projection that sort of tries to balance it. It still has a distortion both in area and in shape, right? But it's more balanced. The last type of projection I want to mention, because this is one you will see, and it's a useful one. It's called equidistant projection. So like here on this example, it's an azimuthal equidistant projection. So you pick a point, in this case Athens, right? And that's the center of the map. And like if you measure in a straight line away from Athens, okay, you will always be able to get a straight line equal distant to the point you're trying to measure to. And so that's really handy, if you're trying to calculate great circle routes or distances to things. Okay, so that's a little refresher on map projections. And I'm going to stop the share here and bring up ArcMap so we can kind of see how projections work in GIS. And it's actually, pretty simple. They've built in a lot of intelligence into the system. Believe me, this could get into some ugly mathematics, but they have, really worked this out and automated the process for us. So this example I'm working from is from Getting to Know ArcGIS, and this is exercise 13A if you're following along and want to access the data. And what you can see here is I have a blank layout. So I'm in layout view here now. I'm not in data view. And there's actually 3 different windows here. So we're going to make a map showing U.S. population growth, and this is something that we might be interested in for our project. We probably won't show the whole U.S., but we might want to do a projection showing population growth in Oklahoma. At any rate, we have this window here, which is for the lower 48 states. Alaska and Hawaii have their own data frames because they're way off geographically, right? And so this is, you'll see this is a very common way of showing the U.S. with the lower 48 and then insets for Alaska and Hawaii. And so you can see here over in the table of contents, we've got 3 data frames. Okay, so what I want to do now is I don't have any data in here. So I've got the lower 48 data frame activated. I'm going over to my catalog here, and I'm in chapter 13 here. And if I hit the little plus sign and look at data, I've got two shape files and two layers, okay? And so what I want to do is I want to bring in some data for our maps. But before I do that, I want to kind of illustrate here in ARC catalog. So I'm going to click on states layer there, and I'm going to right click. I'm going to get the item description here. And so you can see this is like our metadata that we've seen before. We don't have a thumbnail made for whatever reason. And they're really not much showing here because it's a layer file. But if I hit preview, you can see and it contains all 50 states, right? And you can see it has you know, it kind of a stretched out, distorted look to it, right? And Texas and Montana look to be about the same size, where in reality, Texas is twice as large as Montana, right? Things like that. We can also hit the little table view here. And in our table of data, you're going to see we have the state names, and then we have the population from the 1990 census, the 2000 census, and a numerical change there and a percentage change, right? So we can show all this, you know, on our map. All right. Now, going back to the catalog here, I'm just going to right click on my shapefile here that goes with that layer file, and I'm going to get its item description, right? And now you see the same thing really that we were looking at, except that you know, it doesn't have the symbology on it. Last thing I'm going to do is I'm going to go over here to the catalog. I'm going to right click on shapes layer and get its properties. And there's a general tab, but I'm interested in the XY coordinate system tab. And this will tell us what coordinate system we're using, right? And so in this case, we're using a geographic coordinate system. That's GCS. You know, usually see that. And then it's a North American, I'm sorry, this isn't my favorites, but it's the same thing down here. GCS North American from 1983. And don't be shocked if you see some old coordinate systems, right? A lot of times these things are developed and they're used from then on. I mean, I've seen them go back into the early 1900s, and they're still perfectly good, right? At any rate, we just want to make sure, you know, we know what we're dealing with here. So I'm going to hit OK there. And now what I'm ready to do is to bring some data in here. So I'm going to bring the states layer into lower 48, okay? And then here you go. Here, so here you can see, and it kind of cropped it off here, and the lower 48, and it's kind of, you know, shifted. And that's kind of to be expected. And they have saved a bookmark for us called the lower 48. If I click on that, now it will fit the 48 states in to the layout window, the data frame, and you can see here that you know, this is not what we're used to seeing when we look at a map. Like if you look at the red and blue states on election night, you know, it doesn't look distorted like this. You know, where it seems like Maine is drooping its head, right? And so the reason that it looks like this, you know, is due to the map projection, okay? And so what we want to do here is basically change it from this geographic coordinate system to a projected coordinate system. Now, to do this, I'm going to double click on the data frame here, and you'll see there's a bunch of tabs. And so the coordinate system comes up where you can see it's the GCS North American. And I'm going to go here and hit the little plus sign next to projected coordinate system. And there's a bunch of them, right? But, this is a pretty big map. So I'm not looking like, I'm looking for something continental in scale. You'll notice that we have state plane and state systems down here. These would be more appropriate for if we were just doing Oklahoma, and we might use those in our work later on. But anyway, for now, I'm just going to do continental, and then I'm looking for North America. And then you have a bunch here, and there's, you say, well, geez, Sean, which one do I pick? Well, maybe you know something about cartography, but in this case, I'm just kind of looking, it's like, well, I would like an equal area a projection. So we've got a conic view here, and conic is very common if you want your line to follow a parallel that goes through your area, in this case, the United States. So we'll just try that contiguous Albers equal area conic, and we'll hit OK. And there you go. Now you see, oh, that looks more like what I'm used to seeing. And we got a bookmark here after the projection. Now they've got in this file, they've got these bookmarks handily made for us. But if you didn't have this, all I'm doing is zooming in, right, or zooming and panning, right, to get it centered. So anyway, there's a nice view of the United States, and so we're all good to go there. Except we're missing Alaska and Hawaii. So we're going to do a similar thing for them, right? So I'm going to right-click on Alaska and activate that data frame. I'm going to go over to the catalog, and I'm going to add that states layer to Alaska. And once again, you see the whole thing here, and we want to change the data frame to just focus on Alaska, okay? And so once again, I'm going to go in here, I'm going to select a projected coordinate system, and I'm going to select continental, North American. In this case, I'm just going to get the Alaska Albers equal conic, right? Equal area conic. And there you see how it rotated it, right? So this is the same projection, but now it's centered more on Alaska. And I got a bookmark there for Alaska. So there you go, right? And then we're going to do the same thing on Hawaii. So I double clicked on the data frame there to activate it. I'm going to drag in the states layer into Hawaii. And this is now, old hat. We're doing the same thing, projected coordinate system, continental, America, Hawaii. Okay. And bookmark Hawaii, right? So now we got a nice map that shows the United States, and they're all projected in this using that Albers conic equal area projection, and it all looks nice. And we're ready, to export or print our map. Now, before we end here, I want to point out that sometimes all of this data had projections, right? And so what if we get a layer that doesn't have a projection? It's unknown projection, right? Well, let's go back here and activate lower 48 again, and I'm going to go over to Arc Catalog. And I'm going to add this Fast Cities layer. I'm going to bring it in. And it didn't do it. I didn't think this one had a coordinate system attached to it. Let me try. That's interesting. The shape file. Yeah. We're all good to go. All right. Well, I'll just have to explain this. I thought this wouldn't have a spatial reference, right? And so what happens is if you get a layer that doesn't have a spatial reference, what's going to happen is you'll get an error message that says, there's this data cannot be projected. It has an unknown spatial reference, and so it can't be projected on the fly. And so what happens then is it tries to bring in the data, but oftentimes the data, it might be, you might think it's missing because it's so far off the map that you can't see it, or you may find that things are not lining up very well. And so in this case, it did line up. So I don't get to show you that, right? But if you did, I will show you that if you do get that, the way to remedy that is to go up to Arc Toolbox and open up Data Management Tools and go to Projections and Transformations and go to Define Projection. And then you're going to input, which feature class you want to use. So we're going to use Vast Cities layer. I see, it's already got a coordinate system, and so. But if it didn't and we wanted to change it, we could click on it here, and you'll notice that this is the projected coordinates system, and you can you define the projection if it didn't already have it. All right, so this was sort of redundant, but I just wanted to show you how you do that if you ever find that you can't project the data, or it projects wrong. You can always go in and define your coordinate system. All right, and then lastly, go up here and activate Alaska, and we hit Vast Cities and bring it in up there, and then we'll do the same thing for Hawaii. Should get Honolulu, right? And everything projected nicely. So anyway, that's sort of an overview of map projections. Map projections is a very extensive topic, right? So I'm basically just showing you, how to change them, how to modify them, or define them if they're missing. But a lot of this is opaque to you. It happens because ArcGIS can do all of these transformations of different layers. So that about covers it for map projections. And next time we're going to focus on geodatabases.